So in this lesson we're going to begin to introduce ourselves to a concept called rotational kinematics. And so what rotational kinematics really is another way of looking at the motion of objects which rotate. If we have this ball and it's rotated a certain distance, we could measure this distance as in how far along this way did it rotate. But that actually varies depending upon where I am on this circle. If I'm here, I've rotated a smaller distance in what I would call the linear distance or the tangential distance than out here. But another way that I can measure this motion is to measure how far did it rotate in terms of an angle we call angular displacement. And this would be the angle that an object rotates through. Now it's worth pointing out that angular displacement in physics is measured in radians. So really this considers angular distance that's been traveled from beginning to end. It's a way of describing how far does an object turn or spin that does not depend upon how far I am away from the center of this object or the center of this rotation. If I've gone from this line to this line, in any point along those two lines, the angular displacement has remained the same, whatever that angle is in radians. Now, if we have a way to talk about angular displacement, we should have a way to talk about velocity, kind of like we had regular displacement, how far does an object travel, and then velocity, how fast and in what direction does it travel. We have a term called angular velocity, which measures how quickly an object spins in terms of how quickly does that angle change. Usually I would think of this as the rate of rotation of an object. How many radians per second does it go through? One way to measure angular velocity, average angular velocity, is the displacement over the time. And there's a relationship between angular velocity and displacement that looks something like this. That angular velocity and angular displacement looks very much like one of our toolbox equations. Now the one thing to point out is that this makes the assumption that angular acceleration is the same, the rate of rotation is constant. So the units here would be radians per second. You'll sometimes see rad per s as a way of measuring that. So let's do a quick example problem. Let's say we have a saw blade and it's going to rotate 300 radians in 2 seconds. We want to calculate what the average angular velocity of the blade is. And so easiest way to do that is angular displacement over time, 300 divided by 2, 150 radians per second. And the second question we have is, what if the blade started at rest and accelerated uniformly? Calculate the final angular velocity. So we'll make use of this equation. Omega 0 is 0. So if we rearrange this a little bit for final omega, divide both sides by t, multiply both sides by 2, subtract the initial velocity, which we know is 0, so you end up with 300 radians per second has to be the final velocity. Now it's worth pointing out that we'll end up with a toolbox of equations for angular kinematics that actually looks pretty similar to a toolbox of equations for regular kinematics. So in the next lesson we'll start to look at our toolbox of equations and what if that rate of rotation is not constant.